The speaker is Sachin Jain from the IJR Pune. Today he will discuss CFT interpretation of correlation function in α-vacua. Please join me in welcoming Sachin. Please start.
Thank you, Jungi, for invitation and this welcome. So I'll be talking about CFT interpretation of correlation function in α-vacua. Just a disclaimer, this will not be like a DSCFT kind of a talk. It is basically calculation of correlation function in α-vacua. The results, what is the interpretation in terms of CFT correlation, CFT symmetries, okay? So this is more like the cosmological bootstrap program rather than the DSCFT thing that I'm interested in, okay? So in this talk, we are mainly concerned with 3D Euclidean CFT correlation function in momentum space and correlation function in α-vacua in de Sitter space. Okay, these are the two things that I am interested in this talk. So what is α-vacua? It is a de Sitter. I'm going to introduce it more detail later, but just to explain the title, that it is de Sitter invariance allows for two-parameter set of vacua, generally termed as α-vacua. Actually, there are two-parameter set of vacua. You can call it alpha-beta vacua, but for simplicity, I'll just refer to it as alpha-vacua. The usual Bunch-Davies vacua that we hear about is one of the points, spatial point in this two-parameter set of vacua, alpha-vacua.
So when you say de Sitter invariance, is it the de Sitter isometry, or what? When you say de Sitter invariance, what does it mean?
Yeah, so de Sitter symmetry, de Sitter, the isometry of the de Sitter is SO1, D. So these are the set of shades which are invariant under those symmetries.
Okay.
So just to define alpha-beta vacua, this is like the Bunch-Davies vacua, and the modes, A dagger modes, they create excitation in the Bunch-Davies vacua. Alpha-beta vacua will be defined by some in this way. It's like some very excited, highly excited state of a Bunch-Davies vacua. And this is something like squeezed state kind of thing that we might have seen. You might have seen. Speciality of this is that this is invariant under de Sitter isometry group, and this was discussed in a classic paper by Allen and separately by the Motola.
So I have another question. This
yes,
the definition of the α-vacua. So
yeah,
sometimes people using this alpha depend on also mode K. So like you only interested this alpha and beta, but in principle some people interested this alpha K, which depend on the momentum. I'm not sure that is invariant under this DS isometry, but here are you only restrict to this one alpha, or in principle you can extend to any alpha K?
So alpha actually goes, you can take it to be 0 to infinity, and beta goes from -pi to +pi, let's say. But these are all constant value, not dependent on K. If it depends on K, I think it will be difficult to make it a isometry. That I have not checked, but I believe that it will be difficult to make it a isometry.
Okay, thank you.
Okay. So just to give you an analogy, Bunch-Davies vacua is like the Minkowski vacua that we do quantum field theory in, and alpha vacua would be like a squeezed or the highly excited state in that. Okay. aim is to compute 3-point correlation function in this vacua. And they find application in cosmology, and we would like to understand this correlation function in terms of 3-dimensional momentum space CFT correlation function. This is the aim of this talk. Okay, so we would like to calculate correlation functions that I'm going to define in this α-vacua. And then I would like to understand that from a 3-dimensional CFT perspective. Okay. So before going into some more details, so this is the result that we are going to reach at the end of the this discussion, is that the Barnes-Davis vacua, which is a well-known vacua where a lot of calculation has been done, is can be understood in terms of correlation function in Barnes-Davis vacua can be understood in terms of Euclidean 3D CFT correlation function. This is very well understood. This is the using the cosmology or all those things. There has been a lot of paper on this. There are some papers on the calculation of correlation function in α-vacua, but not very systematic. And what I'm going to show in this talk is that Euclidean 3D α-vacua correlation function can be understood again in terms of 3D CFT correlation functions, Euclidean 3D CFT correlation functions, provided I relax the consistency, OPE consistency condition. OPE is just the operator product expansion. Okay, I'm going to explain these terms, but this is what I'm going to reach to. So as you can see, that α-vacua is a much more general answer that I'm going to get. If I impose OP consistency on top of this α-vacua result, I will reach the Barnes-Davis vacua answer. Okay. So I am relaxing OP consistency. You can think about α-vacua as a relaxation of OP consistency condition that give rise to much larger class of correlation function. And then if you impose the OP consistency, then you will get back the Barnes-Davis correlation function. So before I proceed, is there any question or comment about this? Okay. So there are some references. Maldacena Pimentel, one of the classic paper, and then there are several papers by Trivedi et al., which uses this de Sitter isometry to calculate in the cosmological correlation functions. Then there are a set of papers by Skenderis and his collaborators where they just try to understand 3D CFT correlation functions in momentum space. There are also recent works by Baumann et al. And Enrico Payer et al. It's a series of works on trying to understand cosmological. These are the works collectively terminology cosmological bootstrap papers. These references are not complete. Just due to the space, I have not written all possible references. My talk will be mainly based on the paper that appeared recently with Nilay Kundu. He's a faculty member at IIT Kanpur. Suman Kundu and Sunil Sake, they are just graduating from TIFR and going for a postdoc. And Abhishek Mehta, my student, who is in his going to the 5th year, and he will be graduating soon. Other references that will be useful is some of the works that I did recent in last 1 year with a set of collaborators about 3D CFT correlation functions in momentum space. Okay, so as I outlined, so I'm going to first discuss momentum space CFT correlation function. I'll go slow on this part because mostly while learning CFT, we do learn position space or mailing space. CFT in momentum space is not discussed that much. And this discussion will be self-content and no connection to the cosmology will be required for the first half of the discussion. And the second half, I'll try to connect whatever we learn in the CFT to the cosmological correlation functions. So there are some simple motivation why would I like to study momentum space CFT? Of course, cosmology is one example. Then there are a lot of examples, application in quantum matter physics. It also has a very nice connection to the flat space S matrix amplitude. For example, if I start with 3D CFT correlation function, in the flat space limit, it goes over to 4D flat space amplitude. Okay. And this correspondence has actually played very important role in understanding 3D CFT correlation functions. Other thing is that, whenever we do calculation using Feynman diagram, we generally do in momentum space. So it is very important that we understand CFT in momentum space, CFT correlation function in momentum space well. So here is again summary of the motivation. So 3D CFT correlation function in momentum space. This is connected to, as I said, cosmological correlation function. So this will be connected to de-Sitter amplitude in de-Sitter in one higher dimension, in 4-dimensional de-Sitter space. This will also be related to 4D flat space amplitude. This is more or less like this is not exactly in the same spirit, but there is this 4D flat space amplitude and 2D celestial holography that people explored. There the idea is that can you use one or the other to understand something more about the S matrix or the CFT, or vice versa. Here we'll see that exactly same thing will happen here, that there are a lot of even though 3D CFT has been studied for long, this connection will give us a lot of new results, even at the level of 3-point function, which are believed to be well understood, even at the level of 3-point function in 3D CFT correlation functions. Okay.
So in here, the CFT in the DS and the celestial holography, both CFT are do you expect that both CFT are unitary, or DS is a non-unitary, or this?
Yeah. So this actually I will not make any connection. Yeah, this is not. I just wanted to make this. I just wanted to say this connection that there's a similar connection. And this CFT actually very recently there was some paper by Komatsu and collaborators. What they have shown that the notion of unitarity here in this CFT is little different than the usual CFT notion. Okay, and remember that this CFT is inherently Euclidean. Okay, and the notion of unitarity in this CFT is little different than the usual CFT that we study. Okay. Is there any other question? Okay. Now, one question that immediately comes to mind, understanding CFT is important also in momentum space. So then why has it not been actually explored much, or it has not progressed as much as in the Poisson space or in the Mellin space? It turns out that it is technically much more difficult. Even the calculation of 3-point function, which in the Poisson space is very, very easy, it turns out in momentum space, it is actually not very trivial. And also the existing result that people have calculated, they do not actually give much insight. However, the story has changed very recently that I'm going to discuss as I go along. Interestingly, it turns out there exists almost no result for general CFT 4-point function. Only, using, let's say, de-Sitter, people have calculated some tree level exchange and then got certain answer of CFT which are 4-point function. But in general, like in Poisson space, we have a statement that it up to cross ratio, I know the answer. It turns out in momentum space, even making that statement is very, very difficult. Okay. For scalar 4-point function, very recently it was understood how to construct 4-point function of some cross ratios, but it is very, very ugly and not very clean and not very cleanly understood. And even the spinning correlation function, even that statement does not exist. Okay, no, it's very, very difficult to establish such a statement. Other things, as you can imagine, that the contact terms are going to play very, very important role in momentum space CFT. Because imagine momentum space CFT, it's a Fourier, suppose you try to do a Fourier transform of the Poisson space answer. In the Fourier transform, you will do all over the space, you will do all over the space Fourier transform. So clearly, when 2 points, there will be, this integration will also require the information about the contact terms because you are integrating over whole over the space time. So, that also poses a lot of difficulty, and as well as you will, there are also some divergences issues that you need to take into account appropriately. Okay? These are some of the things. I'm just saying that some of the difficulties, and people are slowly making progress along this line. And I'll discuss some of the progress that we were able to also do.
I have one comment. The momentum space calculation, like in higher spin ADS-CFT concept, that can be done, isn't it? Like because the CFT is like there, people consider like when free theory. So free theory, one can calculate this everything so that their momentum like OP and this one is known, isn't it? Right?
Sorry, I could not hear properly, but let me say that, even if you try to do a 4-point function in momentum space, let's say for free theory, you have to, for Poisson space, it's very easy to write down just the answer because, the process you just write down. But in momentum space, if you just try to get the 4-point function, you have to do very non-trivial integrations. And, those are like box diagram calculation, which in 4D, we know how hard they are. In 3D, maybe 3D you would be able to do it, but as you can see that it's already quite difficult actually to actually get a expression as compared to the Poisson space.
But the CFT is free, so that you can in principle calculate everything, so that it's already known, isn't it? Like in the momentum space OP or this kind of thing, this structure.
Somehow I'm not able to hear you properly, but I think only the 4-point function you can calculate. As I said, like you can calculate, let's say TTTT, you can calculate, but the calculation itself becomes very, very messy and very, very difficult. But in principle, you can calculate. Okay, so that is what you can do. In principle, you can calculate, but the calculation is messy, not as easy as the free theory calculation. But understanding the OP and then the expansion due to this block expansion, those things I'm not sure how much they have been understood. As of
yes, but so that's true. But because we did in the using the component partial wave function and some using the momentum space in the extra operator, we did some calculation because it was possible in the free, but of course I agree that the interacting case is horrible. But anyway, this is just comment.
Okay, thank you. Yeah, so before going to the details of the momentum space CFT, I would like to very quickly remind some of the features of the Poisson space CFT Poisson functions. The 2-point function, as we know, is very, this is what it is given by. The 3-point function is given by this formula. Here, I would like to emphasize, in order to obtain this 3-point function of the scalar 3-point function, we only needed, Lorentz invariance, translation invariance, Lorentz invariance, and the scaling symmetry. We did not need any other thing, neither spatial conformal transformation or that this 3-point function has to be consistent with OPE expansion. No such thing. Just this much amount of symmetry was sufficient to determine the 3-point function. I'm making these comments because this will be useful later in the momentum space. Okay. Now you can check that automatically the result that you get, this result is actually consistent with the consistent in the OP limit, in the sense that if you take 2 of the operators close by, the result that you get is consistent with the OP expansion. That is a well-known thing. So in Poisson space, there is no such issue. You just write down an answer and it is consistent with the OPE expansion. Okay, by OPE expansion, I mean that I bring two operator close together and then write down the whatever result I get, I want to reproduce it by using the OPE expansion. Okay. Now coming to the spinning correlator in the Poisson space, we focus on the conserved currents, and that is what will be useful in this in the context that we are interested in. For spinning correlator, to calculate 2 and 3 point function, what you do is that you go to the embedding space. In the embedding space, conformal invariance just becomes like the Lorentz invariance. You write down Lorentz invariant quantities in terms of Lorentz invariant quantities in the embedding space coordinates, and then you just have to impose. You write down all possible structures, spin structures that are allowed. Let's say you are calculating TJJ, this 3 point function. You write down all possible structures, and then you impose this word identity. As you can see, if you work at a separated point, this right-hand side can be set to 0. So that's your choice. If you work at a separated point, right-hand side can be set to 0, and then you wrote down based on symmetry all possible structure, and then you impose this symmetry and find out what is your result. Okay, and this was done in a paper by Gyombi in Prakash. What they saw that in 3D CFT, if you do this for conserved currents with some restrictions, you generally get 2 parity even part of the correlator and 1 parity odd structure. Okay, the parity even structure can always be computed in the free theory, such as using free bosonic theory and the free fermionic theory, whereas the parity odd structure cannot be obtained in a free theory. So these are the results that were obtained in the Poisson space. Okay. Let us now come to, after reviewing this Poisson space answer, let us now come to the momentum space analysis. One can say that I would like, one can do a simple Fourier transform, but as I said, there are issues of contact terms, etc., and also doing that thing becomes really complicated. One rather imposes directly the conformal word identity directly in the momentum space, okay, and solves the correlation function as a solution to those conformal word identity. And this is the comment I already made, that unlike in the Poisson space, in momentum space, there is no notion of separated point, because I'm working in I'm doing a Fourier transform, so integration over whole space time. So it makes things a little difficult. Okay, so I'm going to now discuss what are conformal word identities in momentum space very briefly. So in Poisson space, conformal word identities look like this. This is the dilatation word identity. This is a first order differential equation. Spatial conformal transformation is also a first order equation. As you can see, there are 2 x's present here. So if I do a Fourier transform, it will become a second order differential equation, because x roughly can be thought of as a del del p each x. So in fact, if you do that, you will find that the dilatation word identity remains first order, but the SCT transformation, that becomes a second order differential equation to solve. Okay. If you have spinning correlator instead of the scalar, then there is one more extra piece that you get, which you can ignore for the moment. But what I just wanted to emphasize is that here you get second order differential equation rather than a first order differential equation. So now we are just going to solve one example for scalar 3 point function k kappa, which is a spatial conformal transformation acting on this 3 point function has to be 0. That is the conformal invariance. I'm going to define Pj as the mod of Pj. This is all I'm doing equilibrium, so I can take the square root. So wherever there is a not a bold, if it is not bold, then this is the symbol. Okay, Pj is equal to mod of Pj, mod Pj, square root of mod Pj square. This is the dilatation word identity, and if you write down the spatial conformal word identity, they give you two different equations. Okay, the reason is here spatial conformal transformation was a vector equation, vector Roth equation. So you use a momentum conservation for 3-point function, and if you use momentum conservation for 3-point function, only two momentums will be independent, and you will get two equations. Okay. So you see these are two equations, two second order differential equation. Now using the symmetry that it is scale invariant, etc., you can write down an ansatz of this 3-point function of the following form, that there's an overall scaling factor, and you bring out the factors p1 square by p3 square. These are the variables that you would like to solve for. Okay. Because these are second order differential equation, and there are two second order differential equations, you will get actually 4 solutions. Okay, you will not get one solution as you got in the Poisson space, but here you are going to get 4 different solutions, and these 4 different solutions will correspond to these mu values. Will be mu is equal to 0 or delta 1 minus 3 by 2, and delta is equal to this comes out of a little calculation, and delta t is equal to delta 1 plus delta 2 plus delta 3. Okay, this comes out of a little calculation. And then what you do is that using this value, then you just try to solve for G. I'm going to show you an example, okay, concrete example. Remember that in Poisson space for scalar 3-point function, there was only one solution that we got. We did not get 4 different solutions. And there we just, by demanding scale invariance and the Lorentz invariance, that gave us a unique answer. We did not have any further choice. To give you an example, if I take the scalar operators to be having dimension delta 1, delta 2, and delta 3 to be 3, the answer, this R is just theta, the 3-point function of 3 operators or with the dimension. I'm just writing it for writing as a R just for convenience. This takes this form, okay, where Ka sum over 1 to 3. Here all the Ka are the mod, okay. So Ka is basically, as I said, mod Ka or square root Ka square. Okay. And the other 3 solutions are obtained by just making this K, by K3 to minus K3, K2 to minus K2, and K1 to minus K1. Okay. So you get these 4 solutions. So instead of one solution, what you get in momentum space, you get there are 4 solutions, and the most general solution you get is a sum over these 4 solutions: A1, R1, A2, R2, A3, R3, A4, R4. So you get 4 parameters rather than 1 parameter. Okay. However, in Poisson space, we saw that the answer that we got just by doing scaling and the Lorentz invariance was automatically consistent with the OPE limit. If we demand that our answer, the 3-point function in momentum space, should also be consistent with the OPE limit, we'll see that out of this 4 solutions, this A2, A3, and A4, R2, R3, R4 has to vanish, and you will only be left with R1 solution. And you can check that actually that is the true, and that is consistent with the Poisson space answer. Okay. So what I'm just trying to say, that if you have this 4 solution, this is what the momentum space allows for you. If you impose OPE consistency condition, then you just restrict to one solution, which is equivalent to Poisson space. So I would like to mention once more that the chain of inputs that is there in Poisson space and in the momentum space, they are a little different. In Poisson space, this OPE thing was automatic. You did not have to input. But in momentum space, it was not automatic, and you had to input it in order to reduce the answer. So this OPE limit, which is in the Poisson space x2 goes to x3, can be shown to imply that K2 and mod K2 and mod K3 are of the same order, but it is much, much, much greater than the mod K1. Okay. If you want to see the details, you will find it in Mandasan pimental paper. But you can show it, it's not very difficult to show. You can show that the OPE limit in Poisson space, where I bring 2 points close together, correspond to this limit in the momentum space. And you can check very easily that in this limit, if you do a series expansion of the answers here, now after doing a series expansion, you can now do very easily a Fourier transform. And you will see that the only R1 answer is consistent with the Poisson space singularity. Other things are either more singular or less singular. Okay. So you will throw away this answer. So you will just keep this R1 answer. One more thing that would be useful to keep in mind, this R1 had a log singularity in E, where E was mod K1 plus mod K2 plus mod K3. As you can see, R2 will have a log singularity with one of the signs flipped. K3 will be minus K3 here. K3 will be minus K3 here. For R3, K2 will be minus K2. So except R1, all the other things will have singularity, which will have, in general, if you calculate, you will see that only the solutions which are consistent with the Poisson space will always have this kind of singularity. But whereas the answers which are not consistent with the Poisson space will have other kinds of singularity. Okay. This is an important point to keep in mind. Okay. So now what we have found that if we, after getting a momentum space answer, if I demand that it has to be consistent with the OPE limit, then I get a unique answer. And it turns out that if you calculate that, I'm going to come to later, but if you calculate the correlation function in Bunch-Davies vacua, you exactly reproduce this R1. Okay. So the picture is that momentum space CFT correlation function, if you impose OPE consistency, then what you get is actually the Bunch-Davies correlation functions. Okay. Now, what I'm going to do is, which does not have any analog in the Poisson space, but I'm going to do the following, that I'm going to relax this consistency with the OPE limit. If I relax the consistency with this OPE limit, the most general solution is A1R, this is R1. R1 I have written as A of RK1, K2, K3. R2 is of minus K1, K2, K3. So, other places there is a flip of the sign of the momentum. Okay. Now, this left-hand side is a permutation symmetry invariant, right? Under 1, 2, 3, all of them are scaling dimension same, delta, 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 all of them are 3. So this left-hand side is permutation invariant. So the right-hand side should also be permutation invariant. Let me investigate looking at this explicit answer. So if I look at RK1, K2, K3 without the minus signs here, just RK1, K2, K3, you can easily see that this is by itself permutation symmetry invariant. This is by itself permutation symmetry invariant. All these quantities are permutation symmetry invariant. But if you make R of minus K1, let's say, these three solutions will go under each other if you do permutation among each other. Okay. So if you demand permutation symmetry, then from the 4 parameter set of solutions, you immediately reach a 2 parameter set of solutions. So here you get A1 and A2 multiply with this R with a minus K2, R with minus K2. Okay. So you see that demanding permutation symmetry takes you from 4 parameter to 2 parameter. As I'm going to discuss later, but just a spoiler, you will see that if you calculate correlation function in the α-vacua in Dissident space, you will precisely, you remember there were 2 parameters, alpha and beta, 2 parameters. You will precisely, there will be a map between these 2 parameters, A1 and A2, and this alpha and beta parameter. Okay. And you will see that the α-vacua correlation function precisely takes this form. Okay. So that's the reason. So that was what I was just showing in the one of the final result slide, that if you relax the consistency with the OPE expansion, the result that you will get will be exactly same as the result if you calculate the correlation function in Dissident space in the α-vacua or alpha-beta vacua. Okay. So rest of the talk, here is the outline. We have discussed the CFT correlator for scalar operator. We now will briefly discuss the correlation function in Dissident space. And then whatever I said in this one point here, I'm going to make those connections a little better. And then at the end, I'm going to come to the spinning correlator, which are a little more interesting than the scalar correlator. Is there any question or comment at this stage?
So in momentum space, so there are 4 independent solutions for scalar 3-point functions.
Yes.
And so if you consider 3-point function with non-zero spin like spin 1 field, so what is the number of independent solutions? Is there a general formula?
Yeah, we are going to discuss this. For example, if you calculate, let's say TOO, let's say this is spin 2 and 2 scalar, you will see that there are 3 solutions that you will get. Okay. Whereas in Poisson space, you just get only 1 solution. Okay.
Okay.
I'm going to come to this, and you can actually, for example, you can actually count this thing more systematically for arbitrary spin S1, S2, S3. Directly doing it in momentum space becomes a bit difficult. You have to go to the spinor helicity variables, and then in spinor helicity variable, it becomes a little easier to calculate, and then there it is easy to actually, very easy to count how many independent structures are there.
Okay. And can you discuss the correlation functions of fermion?
Say again, please.
So can you consider the correlation functions of fermion? So fermion field, not bosonic.
Fermion operator, you mean?
Yeah. For example, can you consider momentum space correlation functions of fermionic fields?
Right. By fermionic field, you mean fermionic operator, right? Because even if I have, let's say, psi bar del psi free field, free fermionic field, I can construct operator of this form. This will be scalar, but I suppose you want like the fermionic operator, which will have, for example, which will have spin half kind of thing, right? That's what you want.
Yeah. For example.
Yeah. Just 1 second. My charger is not charge has reduced. 1 second, please. Yeah. Okay. Sorry. Yes. So actually, directly by solving conformal word identity, I have not done it. I think no one has done it. But I suppose in super conformal theories, people have calculated this correlation functions. Okay, in momentum space.
The 3-point function, isn't it general like a 3-point function of the fermion?
No, yeah, exactly. You are right. But what I was thinking that, let's say I have 2 fermionic field and 1 spin 1. This kind of thing will be non-zero. This is what I have in mind. Of course, this will be 0. Yes.
Okay. Thank you.
Okay. Now, let me come to cosmological correlation function calculation. This everyone knows. I just want to just restate once more. So there was an inflation, and then some reheating happened, and then slowly after some time there was a CMB background that we get CMB surface, and then due to some anisotropy in the CMB background, slowly those anisotropies clumped together, and then they gave rise to the large-scale structures that we get. And inflation very successfully explains all the observed approximate isometry and homogeneity. Small quantum fluctuation leads to anisotropy in CMB, and it leads to formation of large-scale structures. During inflation, universe was approximately de Sitter, and the symmetric group was SO1, 4. The question that this cosmological bootstrap program or calculation of this correlation functions, people ask, what is the constraint imposed by this symmetry on the quantum fluctuation generated during this inflation? Okay. The observables are the correlation functions of scalar or tensor fluctuations on the CMB surface. Okay, those are the things that we observe. For example, 2-point function of temperature fluctuation, which is related to maybe the scalar fluctuation, those are actually observed. Okay, no 3-point function, 4-point function, those things has not yet been observed, but the 2-point function is very well observed. So roughly the picture is the following, that this CMB is somewhere even far away in time, but at the end of the inflation, where you had approximately Dissident space, the CMB correlation function that we are interested in is determined by the correlation function in the boundary of the Dissident space. Okay. So what we will be interested in is the calculation of correlation functions of various fluctuations on the various fluctuations on the boundary of the Dissident space. And there is a well-defined prescription how to convert this fluctuations of bulk field in the Dissident to the correlation function of the CFT correlators that I was talking just a little while ago. Just I want to emphasize here, we are not doing DS CFT correspondence. What we are just going to use is the symmetries of Dissident as it asymptotes to Dissident boundary. We are not going to use any Dissident CFT correspondence. Okay. This correlation function in Dissident actually gives a window to understand initial state or the initial conditions of the universe. One generally takes the initial state to be the Bunch-Davies vacua. This is well motivated, as at very, very large scale, Bunch-Davies vacua behaves like Minkowski vacua. However, there can be various other inflationary scenarios, such as the initial state is a alpha vacua. At arbitrary short distances, these vacua are like the squeezed or the highly excited states, not like the Minkowski space. Okay. There has been a lot of debate about consistency of the alpha vacua, whether is it consistent to consider this calculation in alpha vacua or not. There are a lot of debate about it. There are a lot of argument that it is all fine. For example, you will find in this paper that they commented that the Dissident alpha vacua perfectly works fine. But there are other papers which discusses and shows that it is not at all really consistent. So there's a lot of debate about whether the consistency of this alpha vacua thing. They are also phenomenological. Alpha vacua correlation functions are also phenomenologically very relevant because they can give rise to very large signals. Okay, much larger than the signals in the Bunch-Davies vacua. For a recent discussion, see this paper that came very by Kano and Sasaki very recently. So in this talk, we will not be actually discussing these issues. We'll leave these issues, but what our aim would be that calculation of alpha vacua correlation function, and can I interpret them in terms of the CFT correlation function or not? That's the aim of this talk.
Can I ask one question on that slide? Maybe
Yes,
my question is not so relevant to your question, your talk, but here people talk about the Dissident or quasi-Dissident. Like it's not exactly Dissident, but after the inflation, it's not some close to Dissident, but not Dissident. Like there could be many models. For alpha vacua, is there also similar some analogs plus some quasi alpha vacua vacuum, or like it's not exactly Dissident? Yeah, so that's why it's not relevant to your talk, but because of this slide, I want to just ask.
Right.
I remember that this cosmological correlator, this story, people also trying to understand this quasi-Dissident. So you study this alpha vacua for the cosmological correlator. So that's why I asked.
No, that's a very important question. In fact, I'll have this is one of the things that I mentioned in my last slide, but So the point, as you were saying, that during the inflation, even though it's very slow, potential is changing slowly, and then it's not totally constant. So it is not really a de Sitter space. It's quasi de Sitter space during the. So one needs to take into account that effect in your calculation, and people have done for bunch-Davis vacua, but in α-vacua, there is one way to calculate those effects is that you do the calculation. For example, if you want to calculate 3-point function in the quasi de Sitter space, what you do is that you do 4-point function calculation in pure de Sitter space, okay? And then from there is a prescription to get the correlation function in quasi de Sitter space. So so what people do is that, let's say you have 4-point function calculation. Suppose you have calculated, you put one of the legs to be of the background, okay, in terms of the background field, and then what you obtained is actually a calculation of 3-point function in the quasi de Sitter space. That has been done in the bunch-Davis vacua. I suppose you can do the same in the α-vacua. All you have to do is calculation is still in the using all the properties of the de Sitter space, but at the end you have to do this. So that systematics has not been done yet.
Okay, thank you very much.
Okay. So now I'm going to go very quickly over how to calculate correlation function in de Sitter space. So de Sitter space, all of us know, is this form. And then let's say I have scalar fluctuations during inflation. The action, I'm writing a massless scalar field action here. The bunch-Davis vacua. So if I quantize these fluctuations, this is the mode expansion as we do in the flat space, and then this is how I define the bunch-Davis vacua. That the AK acting on the Minkowski vacua should be 0. And in terms of this AK, the α-beta vacua, which I wrote down earlier, is just defined by this quantity. Okay. Is there a question? No? Okay.
No.
Okay. You can also consider metric fluctuations. That is also possible during due to inflation. And you can similarly define bunch-Davis vacua for the metric fluctuation. And also you can define α-beta vacua. For metric fluctuation, you can in principle write down a vacua which is alpha tilde beta tilde vacua. There is no reason that the α-beta vacua parameters for the metric fluctuation will be identical to this same α-beta of the scalar fluctuations. Okay, they can be, you can define for the metric fluctuation your α-beta vacua separately. You can define with the separate parameters, and you can define for the scalar fluctuation separately. If you have a photon fluctuation, you can also define separately. This point will be important a little later, but I just wanted to emphasize this point. Okay.
Here I have a question. So
yes, yeah.
So metric fluctuation. So in this digital space, you will have a cosmological horizon. So do you also impose boundary condition on that? And the another question is, when you have alpha vacua, is there any change on this cosmological horizon?
Actually, that's a very good point. And you see, what happens is that if you calculate this, I'm assuming as a background field, okay? And sorry, probe field. If you calculate what is the back reaction of this probe field in this α-vacua thing, what you will find out that you can calculate the stress energy tensor. And then what you will find actually in α-vacua, they tend to diverge. And you need to really regulate those divergences. If you and you will see that, and all the you would require non-local counter terms to regulate those divergences, and that is where all the issue comes about. And For example, the other boundary that you are talking about, you will see that you would require the other boundary to actually. So here, even though I'm doing in the point array patch, but suppose you are doing in the full global decider, you will see that the counter terms that you would require the information of the other boundary also. Okay, and that is a part of the difficulty in dealing with this kind of computations. Sorry, did I understand your question? Because your voice somehow I'm understanding other voice, but your voice is not coming very clearly.
No, that's the answer the part of question. Yeah, you can go ahead. Yeah. Thank you.
Okay. So in order to calculate these correlation functions of the fluctuations, what you do is, so in decider space, as I described, a little while ago, I'm interested in correlation functions which are not in-out kind of thing. That is what we are interested in a flat space. Generally, I define in state and then I define out state. This is not the kind of calculation I'm interested in. My observables are on a CNV surface, that is at a particular constant time, let's say. So every calculation, I call it as a particular time surface. So this will be in kind of calculation rather than in-out kind of calculation. And the way to calculate, there is a well-defined in calculation. Here I have just shown, this is a simple formula which actually describes the in calculation. That you use this, this kind of calculation we do always in the flat space, where we use this kind of formula to calculate the S matrix. But here we are interested in kind of calculation. So we use this in formalism to calculate correlation functions of these fluctuations in the decider space. Okay. For example,
for making sure. So
yeah,
here decider is Lorentzian, but this CFT you are talking about is Euclidean, right? Because is it correct?
Yes. Yeah. Okay. So decider symmetry, as you can see, so decider is SO 1, D. That will be the Euclidean CFT.
Okay.
Yeah. Now, if you calculate, you can calculate the correlation function of these fluctuations, and then you can actually convert those calculations to a calculation of operators that I spoke about earlier. For example, if you calculate 2-point function of the scalar fluctuation, you can relate it to the 2-point function of the scalar operator. And for alpha beta vacua, you will get this 2-point function, okay? That it just becomes, this is for massless field, that is what we consider del mu phi square. It will correspond to delta is equal to 3 scalar operator. And then, this will become, this is the calculation that it will become, okay? This is the result that we will get. So you see the alpha beta vacua parameters come here. Now, as you can see, if you set alpha and beta to 0, everything just becomes 1. Okay, so that is the Bunch-Davies vector. That is the normalization that we have chosen. Now, if you calculate TT 2-point function, you can also calculate the TT 2-point function using the same prescription. You will get this kind of. This is the polarization tensor, which accounts for the spin of the stress tensor, and you will get this 2-point function. Where here you see here I have kept the alpha tilde and beta tilde here. Okay.
I have another question. Sorry.
Yeah, please.
In the previous slide, 2-point function you can always normalize in certain way. So this 1 over cosine 2 alpha, can it?
Yes.
Do you get that factor because you're choosing some particular normalization? So what kind of normalization?
Right. I can choose any normalization as you pointed out, but normalization I'm choosing is that if I set alpha and beta to 0. That is what I defined as my Bunch-Davies vector. Okay. Okay. So I want to, if I set alpha beta to 0 and I'm using the normalization that in the Bunch-Davies vector, O is just K2 cube. That's suppose the normalization I'm choosing. Then this will be fixed like this.
Okay.
Now you can calculate the 3-point function of the fluctuation. So if you have phi cube interaction and use in formalism, you will exactly get the answer that I pointed out earlier by from the CFT cohesion function calculation. By relaxing the OP constant, the answer that I got earlier is precise in this calculation. And as you can see, if I impose OP consistency, R2, R3, and R4 vanished, you can show from here that, if you just set alpha to 0, you see that if I set alpha to 0, alpha and beta to 0, this B also vanishes. Okay. So you just get back R1, which is what we wanted, that the answer should reduce to the Bunch-Davies-Vacua answer if I set alpha beta to 0, and that should be consistent. Okay. So from CFT, that's what we expect, that if I impose OP consistency, then the B should vanish. This thing should vanish, which correspond to setting alpha to 0. Okay. And then you see that the B vanishes. So this is one consistency that you can check. Now, there was a question of the spinning thing. That's what I'm going to now answer. The spinning case, if you want to calculate the spin 3-point function, the simplest is TOO, graviton, which is related to graviton scalar fluctuation. You will get, again, this is the structure. By doing just the Dissident calculation, you will get the following structure. Okay, A times TOO R1, B times this calculation. And these are the full set of R1, R2, R3 that is I have written. As you can see, this R1 again is just function of K1 plus K2 plus K3. And R2, R3, R4 can be obtained by switching K1 to minus K1, etc., etc. Okay. This you get by directly doing the Dissident calculation. Okay. We have not yet done the CFT of the TOO. However, one thing I just want to remind you, here for TOO, I could have taken the graviton fluctuation alpha tilde and beta tilde to be different, but for the moment I have taken them to be the identical for simplicity. Then you see I have only two parameters, A and B, and these are precisely the same two parameters that appeared in the scalar. Okay. Now in CFT it has a very simple interpretation. You take O3, 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 the 3-point function that we calculated in α-vacua, and then use spin raising dimension raising operator to act on O3, 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 and you will precisely get that the answer for TO3, O3 that you get precisely matches with the answer that you get by doing the alpha beta vacuum calculus.
So question about the notation. So I thought
Yes.
your momenta K1, K2, K3, those are 4 vector. Am I right? Because it is TS4.
Yeah, right. Sorry. I should say this. Yeah, you're right. So let
And then
me
what is the
just say,
Z1 dot K2? Z was a spin structure you said, something like that, right? But what is the dot means there?
yeah, let me explain this in a minute. So what happens is that the fields that I have taken in Dissident are all massless fields. Okay.
Okay.
I have taken either massless particle or so K0 square is equal to K1 square plus K2 square plus K3 square. And this quantity is what I'm calling it to be mod of K square. Okay.
However, when we talk about the green function, usually we are not on mass shell, right? The momenta will be usually off mass shell. So I guess momenta can be any. So why do you impose the on shell condition for the momenta?
What condition? I'm sorry.
So I thought,
This
when you transform to when you calculate the correlation function in the momentum space, I thought
Yeah.
the momenta is the general momenta, not specifically on shell. Am I right or wrong?
No, you are absolutely right. So
And
sorry,
the K square K0 square doesn't have to be a K spatial part square, because
That's right.
we should
So-
not impose any massless condition for the momenta, right?
That's right. Let me just explain. What is happening is that we are trying to relate the d-sitter fluctuation to the CFT cohesion functions. D-sitter is in 4 dimensions. Those modes are really in 4 dimensions, whereas the CFTs are in 3 dimensions. So even though this relation is only in the 4 dimension, but there will not be any restriction on this K1, K2, K3, okay, which is a 3-dimensional amplitude and which is the CFT momenta. And there is no, as you pointed out, there is no restrictions on K1, K2, K3 as it should be. That,
I see, because I mean, it's a kind of time slice. It's a fixed time. So that's what you mean by the 3 dimension. So
yes, exactly. Yeah, exactly. That's what. Yeah, I'm calculating the correlation function of the at the boundary of the Dissident space, which is a fixed time slice.
When you in the first stage, when you talk about the correlation function in the spatial coordinate, and you said it is very difficult to rely on the Fourier transform or that kind of thing, right? Straightforward calculation. So all the correlation function you are mentioning is at the fixed time slice or same same time. I'm a little bit confused.
I'm sorry. I should make this clear. There are 2 different things I have done here. First thing is I have done is in the CFT 3-dimensional CFT correlation function calculation in momentum space. There I have put no restrictions on momentum. Okay. Those are only 3 momenta, K1, K2, K3, and there is no restriction on that. But then next I have calculated in Dissident space, which is in 4 dimensions, and I'm calculating in Dissident space on a particular time slice. On that particular time slice, all the correlations behave like a 3-dimensional CFT correlation functions, and that is the connection. So I'm using a time slice only in the Dissident space, not in the CFT.
Okay, thank you. I understood. So the yeah. So actually, then maybe my next question may be meaningless. So I thought you seems to be neglecting the in the Dissident metric. There is some the conformal time dependent prefactor, right? In front of the it's a Dissident 4 is a conformally you wrote a conformally Minkowski, but there's a yeah. There's a 1 over h square eta square. And when you, since you show the cosmology picture, actually everything is evolving, universe is expanding, right? Yeah. So then the distance is or the momenta is whether it's it's whether it's a physical or it's a co-moving or it's all different. There's always some prefactors, right, to compare with the observation. But at this stage, those things are not. So eventually, it will coming in when you relate to the real cosmology, or
for the moment, I really have not dropped any of these factors. In fact, these factors are really, really important for me to actually get all the pole structures that I have got here. They actually come from this 1 over eta square factor. Actually, those play a very, very important role in order to produce these pole structures. Okay, so
but even though I thought you are talking about at the fixed eta the conformal time, right? So it seems that it's just constant vector at this stage. Am I wrong?
Yeah, let me just show you this thing a bit more clearly. So so if you look at this informalism
I see.
You see there is an integration that is there. Okay.
Good. Okay, I understood. Okay, thank you. Okay.
Yeah.
Okay.
So the other question that you asked about this Z's are the polarization tensor which you introduced to take care of the spin, and this projects to the orthogonal basis. Okay, so for example, Zi dot Ki will be just 0. Okay, this is the choice that I made. Okay, so now very quickly, since the time is really up. First thing that I just wanted to point out that, from Dissident calculation, I get this result. You exactly reproduce the same result by doing what is called using a spin raising and dimension raising operator on the O3, O3, O3 that you get by relaxing the OP consistency condition. Okay. And you can actually do this thing very easily for any other coordinator like TTO, TTT, JJO, JJT, all the thing, and it works very, very nicely. And you see that always these two parameters, every coordinators are just determined in terms of this A and B parameter. Let me just emphasize once more, in order to get this relation to these two parameters, I have assumed that the alpha is equal to alpha tilde and beta is equal to beta tilde. The alpha beta vacuum for the metric fluctuation and the stellar fluctuations are identical. Let me do the following, that I'm going to now say that alpha naught is equal to alpha tilde and beta naught is equal to beta tilde. Okay, that's my choice. I can choose that. And if you recalculate this GOO, you get, there are three independent structures. Now, instead of two, in terms of A and B, just to show you once more, here you, when you took alpha is equal to alpha tilde and beta is equal to beta tilde, you got two A and B, but now you will actually get three independent, C1 with R1, C2 with R2, and C3. Okay, there are three independent C1, C2, C3 that you get. The actual result of C1, C2, C3 in terms of this alpha and alpha tilde, beta, beta tilde is very complicated. I have not really written it down. But now the question arises that, if I use spin raising and dimension raising operator, because OOO in CFT was always of the form A times R1 and B times R2 plus R3 plus R4, because I cannot use, there's no, because of the permutation symmetry, there's only two parameter A and B. How can it cannot produce this three parameter solution, just the spin raising and dimension raising. And here is, to resolve this puzzle, that was a question earlier, little earlier it was asked, that how many structures are actually there in CFT, and can I actually systematically count that structure? Jungi, how much time do I have?
You can still have time, like, can you wrap up within the 10 minutes?
10 minutes, yeah, sure. I'll wrap it up in 10 minutes. Okay, so now, in order to answer that question, for TOO, I see from the direct Dissident calculation, there are three parameters, whereas the scalar gave me two parameters, and if I use spin raising, dimension raising, it cannot give me more than two parameters. How can I get then three parameter solutions? In order to answer that question, I need to develop a little bit of momentum space CFT for spinning coordinator, and that is what I'm going to do for the moment. First thing that I want you to make a note in momentum space, that the conservation word identity, the del mu T JJ kind of thing that I wrote there, it was a function of delta of x1 minus x2 and JJ 2-point function. If I convert that into the momentum space, you get something like this. Okay, this is really, this P1 T mu1 is precisely this. I'm just doing a momentum transfer. This is what you get. Okay, this is the first thing that you keep in mind. Second thing is that while solving spinning correlation function, because you can no longer go at a separated point in momentum space, all the contact, all these delta functions are important because you do integration. If you want to solve conformal word identity, these Wattakaze identities play very important role. It will be very clear now why they play a very important role. Because this is a second order differential equation, and right hand side you have something non-zero. You can break up the solutions into homogeneous and non-homogeneous solution to this. Okay, it is very interesting that this way of thinking about 3-point function does not come directly from Poisson space, but in momentum space, over the last year of working on this, we realized that this is a very, very efficient way of writing momentum space cohesion function, which is not very natural from a cohesion space perspective. And I'm going to show why this is very, very natural. So you break up into two pieces, the solution, into homogeneous and the non-homogeneous piece. The non-homogeneous piece saturates the transverse word identity. You see, the non-homogeneous piece, as it is non-homogeneous, it saturates the transverse word identity. And the homogeneous piece actually annihilates, meaning K kappa on the homogeneous is 0, just like we do in the differential equation. In Poisson space, we do not do such a distinction because I can always work at a separate point. So now I would like to solve this homogeneous and non-homogeneous pieces. For non-homogeneous piece, it is important to understand the notion of this Wattakaze identity. And this Watt-Takase identity for conserved quantity, conserved operators are unique, generally unique. And what you can show, if you impose consistency with the OPE consistency, I don't have time to go into the details, but if you impose consistency with the OPE, then you will find that this has precisely two solutions. This has precisely two solutions. This homogeneous part has precisely two solutions. One parity odd homogeneous, one parity even homogeneous. Okay. The other part, which is the non-homogeneous part, will depend on what is there in the right-hand side. For example, if I take JS1, JS2, JS3, the right-hand side, the non-homogeneous part will be proportional to some JS, JS2 point function. If I impose JS, JS2 point function, I know there's a parity even 2-point function that exists. If I write 2-point function to be parity even, you will solve the non-homogeneous part to be parity even. If you consider the JJ 2-point function to be parity odd, then you will get a one non-homogeneous parity odd answer. So you get 2 even, 2 odd, 2 non-homogeneous and 2 homogeneous when you impose consistency with the momentum OPE. And you see, you get total 4 solutions. Whereas in Poisson space, as it is a very well established result that you only get 3 solutions. Okay. So, even in the OPE consistent limit, there seems to be a discrepancy. So is it a really discrepancy? Actually, it turns out to be no, it's not a discrepancy. What happens is that while solving the non-homogeneous, if I take the JJ 2-point function to be parity odd, it turns out that parity odd 2-point function is
Sachin? Is it our problem? Sachin? It's his problem. Yeah. So somehow the connection was.
Yeah.
Okay.
I'll very quickly finish
Okay.
now. It just last slide I'm in. So just 1 or 2 slides I'm in. So so what I wanted to say is that this is not any inconsistency, because the extra structure that you get actually is a contact term. And in order to make this thing totally clean, what you can do is that you can actually go over to the Dissident space. It turns out that this homogeneous space is obtained from homogeneous for TTT. Homogeneous parity even comes from the Weil cube contribution. Non-homogeneous parity even comes from the Einstein gravity. Homogeneous odd comes from the omega square omega tilde. And TTT non-homogeneous odd comes from omega omega tilde. And you can check, actually, this is a contact term. Okay. And this classification actually is as you can see from gravity, this is a very, very natural classification. And this also plays a very important role if I try to make a connection with the CFT coercion function with the flat space amplitude. Okay, so now I'm just going to finish on this slide. So let me come back to the puzzle that we had, that if I relax OPE consistency, TOO, if I try to solve momentum space coercion function by relaxing OPE consistency, you will find that the TOO actually have 3 different answers. Okay. So you get 1 non-homogeneous answer and 2 homogeneous answers. And then you can show that the most general answer is given by this particular combination, C1, C2, C1, one of the answers, C2, another answer, and C3, another answer. And this exactly reproduces the case when alpha was not is equal to alpha tilde and beta is not is equal to beta tilde. And this exactly reproduces the Dissident calculation. So what I just wanted to conclude is that Bunch-Lewis-Vacua is a Euclidean 3D CFT coercion function, but the alpha-Vacua coercion function is something where you actually do not impose OPE consistency condition, and then the correlation function very nicely works out from this way of thinking about the coercion functions. So here there are few future directions. Some of them I have already spoken. I just want to speak on this for a minute. So, this talk was not about DSCFT. In a DSCFT context, there was a paper by Busso, Meloni, Strominger, like roughly 20 years ago, where they wanted to interpret this α-vacua from the CFT perspective. What they saw is that this α-vacua is a one parameter deformation, one parameter family of marginal, if you suppose you start with the Bunch-Davies vacua, you deform that theory by a marginal operator with one parameter. That one parameter, they were able to map it to α-vacua. But, that way of doing is not very, very helpful to calculate the correlation function. It becomes very messy. It will be very interesting to actually make that connection. And in general, this field that, CFT correlation function relation to the fluctuation amplitude, which I did not have much time to talk about, is a very interesting field. And already, this connection has led to very new results in CFT correlation function. For example, double copy relation, etc., which were not understood in Poisson space. Okay, so I'll just sorry for going over time, and I'll thank for this opportunity for giving me opportunity to give this seminar, and thank you for your attendance.
Yeah, thank you very much for the great talk. Please ask question. Yeah, I have one question. It's simple.
Yes.
So here you are talking about the DS4 and the CFT3. Probably this maybe of course 4-dimensional important, but also this DS CFT also talk is on the DS4. But can you also think of the DS3? Like, is it the same like story?
DS3, the problem is in DS3, the symmetry is SL2R symmetry, and there I'm not sure if if the alpha beta, if I'll be able to actually find out the alpha beta vacua. So in fact, for Dissident 3, definitely in momentum space, I'm sure you will get. Sorry, are you talking about Dissident 3 or Dissident 2? I'm sorry. So what did you?
Dissident 3. Yeah.
Dissident 3. Yeah. So you're asking whether or not the alpha vacua exists or not, right? That's the question.
And this correlator or this whole story is almost parallel or something like always the CFT2 is some special. So that's why I'm asking. So.
Yeah, no, the story is little different there, because Dissident 3, what will happen is it will be related to the boundary symmetry will be related to the CFT2, and then it will break up into double copy, 2 copies, and those will behave like CFT1 cross CFT1. And I'm not sure whether there's enough space for it to have the kind of thing that I was able to do, K1 to more minus K1, etc., etc. Whether it is possible to have that kind of freedom to allow alpha vacua or not. I have not really thought about it. Maybe it will exist. Okay.
Okay, thank you. Is there any other question? Let me ask another question. Actually, this is just curiosity, not the really sharp question.
Yes.
So can you also talk about this alpha vacua in the higher spin gravity?
In the higher spin gravity, where your high spin gravity in the Dissident 4? Yeah.
So for example, the CFT is actually higher spin or the holography. So that alpha vacua or all your calculation can be generalized in the higher spin. In the higher spin, people also talk about a lot of this kind of correlator, like in the CFT correlator. So
right. Yeah, for me, from the CFT perspective, it is actually very, very easy to go. I'm going to assume for the moment that the alpha beta vacua exists, and then all the higher spin symmetry is going to say that I have arbitrary high number of spin with del dot js1 to be 0. Okay. Mm-hmm. Now it will be exactly analog of TTT calculation that you suppose you want to calculate any arbitrary 3-point function. We have done it for TTT. You can also do it for arbitrary spin that we have in our paper. The spinor helicity answers are there, okay? And then it is very easy. I think it will not be very difficult to actually write down answer rather than in the bunch-Lewis vacua or the which is considered with the flat space. It will not be very difficult to write down CFT 3-point function which are consistent with this alpha vacua thing.
Okay, thank you very much.
All the things just exist because all it is that there is extra higher spin operator. So and all the things are known. The homogeneous correlation function for 3-point function, those things are known.
Okay, thank you very much. Is there any other question in the online?
There is one comment I want to make in your last question. I think that's a very, very important. That's a very important point, which is the following. I think that it will be a very sharp distinction between alpha vacua with the higher spin versus the bunch-Lewis vacua. In bunch-Lewis vacua, if you calculate parity odd correlation functions, you will see that if S1 plus S2 is let's say less than S3, meaning there's a triangle inequality if it is violated. For example, TOO, the triangle inequality here is violated because S2 plus S3 is less than S1. Okay. In this case, you can show that the parity odd correlation function cannot exist. One way to see this is that if the triangle inequality is violated, then you will see that the OP consistency will also be violated. But in alpha vacua, because you are relaxing that, it might be possible that you can allow for those parity odd thing even outside, but then you have to come up with new interactions that I do not know whether it is possible or not.
Oh, I see. Oh, okay. Yeah, thank you for the comment. Is there any other question in the online? If not, let's thank the speaker again.
Thank you.
And thank you.